All right, so let's finish up talking about how we can use these quaternion things to do three-dimensional rotations. And the idea behind this is actually really clever, and it's really important in in future math. So the idea is if you have a non-commutative algebra, so we said the only thing that's weird about these is that if you multiply them, the order matters. Well, there's a very important thing you can do that only makes sense if you have a non-commutative algebra. So if I have an element, let's say q, then I can make a function which I'm trying to think of what to call it, but anyway, basically I want to, so this function is going to depend on q. If I plug in any x, I'm going to go q x q inverse. Okay. Now for a commutative situation, then this would be silly because, well, I would have qx q inverse, since it's commutative, would be the same as xq q inverse, and q times q inverse is 1, right? So this would just be the do-nothing map in a commutative algebra. But anytime you have something non-commutative, in particular these quaternions, and also you'll see this again when you take linear algebra, this is something very important to do with matrices. Then multiplying by a matrix on one side and then its inverse on the other side becomes a really key thing to understanding what's going on. And well, why do we think we can use this here? Well, let's look at our formula for multiplication again. So if I go x0 plus x naught times y0 plus y naught. So x0, y0, x dot y dot, or sorry, x dot y plus x0 y plus y0 x minus, or sorry, plus x cross y. So the point was, this is the only non-commutative part, right? So everything else, if I switch the x and y, I would get the exact same thing. In particular, if I just look at this real part here, I see that the real part of, let me just call these big X, big Y, x times y is the same as the real part of y times x. So in particular, if I do the real part of this guy here, the qx q inverse, well, because I can flop things around inside a real part, this is the same thing as real part. If, let's say I take these two, move them up front, x q inverse q, and then q inverse q is 1, so this is real part of x. So even though I don't get back x because it's non-commutative, if I just look at the real part and that's it, the real part doesn't change when I do this function. Okay, so here's the point. The point is I can think of R3 as being, well, just the quaternions that have no real part. So the real part of my quaternion is 0. Then, I mean, it usually looks like a real part plus a vector part. So if this real part isn't there, then I get three-dimensional vectors, right? So I can say, okay, well, let's make a function on R3. So if Q is a quaternion, and we're actually going to take it to be a unit quaternion, so that means the Q0 squared plus the vector squared is 1. So, because if I change the length of the quaternion, it doesn't change this map, because, well, all that happens is Q gets bigger, but Q inverse gets smaller, and then that scalar factor cancels out. So there's no loss in saying, okay, we're just going to deal with unit quaternions. So I can think about this as being, well, this is 1, and then 1, 2, 3, 4 dimensions. So this is like the 4-dimensional unit sphere is what I'm looking at here. I can say, okay, for any of these, for any one something, anything in the 4-dimensional unit sphere, I can make a map from R3 to R3 just by saying, okay, well, do Q, and then take X. Well, X is a vector in R3. We'll think about it as being a quaternion that just doesn't have a real part, and do Q inverse. And then that'll give you something else in R3 because I know it doesn't change the real part. So if I started without having a real part, after I do this, I still don't have a real part. Okay. So this is definitely something I can do. Another thing, this quaternion length, so like length of big X is, I didn't show this, but this respects multiplication, meaning that if I do length of big X times big Y, it's the same as if I do the length of X times the length of Y. So that's something you need to check, but anyway, I'm not going to do it right now. So notice if I do the length of my new guy, well, this is, because I can break it up, this is the length of Q times the length of X times the length of Q inverse. Well, I picked Q to be a unit, so this is 1, and Q inverse is also 1. So I get the length of X, right? So not only do I put in something, a vector in R3, and get out a vector in R3, my new vector has the same length, which the buzzword for this, you might have saw this in a high school geometry class, a function that spits out another, if I put in a line and get out a line the same length, it's called an isometry. It doesn't, iso means doesn't change, metry means it doesn't change the meter or the length of the thing. So, and going back to high school geometry, there's basically only 3 isometries. There's translations, rotations, and reflections. Those are all the isometries in the world. So whatever this function is, for every Q, I get this function. It has to be either translation, rotation, or reflection. Which one is it? Well, an easy thing to do is see, well, let's write Q as being its real part plus a vector. Let's see what happens. I mean, this Q is something in R3. Well, let's hit this particular vector with this function, see what happens. Well, I have Q naught plus Q, and then times Q. And then the inverse, since this is a unit guy, the inverse is just Q naught minus Q. Right? Well, let's think about how to multiply guys. This is 0 plus Q. If I multiply these two, I've got Q times 0, that's 0, and then minus Q dot Q. And then for the vector part, Q0, Q, and then Q times 0, and then Q cross Q, which Q cross Q is 0. So that's what I get when I multiply the first two. And then I multiply the last two also. So here's my, this is a real part here. This is, let me call it length of q squared. So I've got q naught times length of q squared. And then I've got that guy dotted with that guy minus, but minus, there's another minus, so minus minus makes a plus. So q naught. So those two are going to cancel. And they should, because we said, hey, if we do this, we know we're not going to get a real part. So that was kind of, we expected that to happen. And then for the vector part, I've got the real thing times the vector here. So minus, that's length of q squared times q, because again, minus minus makes it plus. I've got the real part times the vector here, so that's q0 squared q. And then I've got the cross product, this guy cross that guy, but again, q cross q gives me 0. So really all I get is this here, which is q0 squared plus norm q squared all times q. And again, this is a unit vector, so this whole thing equals 1. So all that to say, if I do this q map on just the vector part of q, I get the vector part of q again. So whatever this map does, it doesn't move the line that goes through the vector q. So we know it has to be a translation, a rotation, or a reflection. Whatever it is, it doesn't move this line. So if it doesn't move that line, it's definitely not a translation. It could be a rotation about that line, or it could be a reflection through the plane that contains the line. I don't want to talk about it right here because it's kind of obvious later on, but this it preserves orientation. So this, if you knew a little bit more math, is obvious, but it's not obvious right now. So I'm not going to talk about it. So anyway, reflections, of course, if you take the mirror image of something, it flips the orientation of it. So whatever this is, it has to be a rotation or reflection, but because it preserves orientation, it's not a reflection. So whatever this map is, it has to be a rotation about the line through Q. So here's the upshot, is that if I take this FQ, this is rotation about the line through the vector Q. And now, so for two reasons, I'm going to stop and do an example. One is in case that was confusing, the example might help. And the other is because it's going to show us how much does it rotate. Okay, so let's say we just take the vector I, and we're going to rotate the vector j. So I need to make I into a quaternion, so I'm going to split part of it off. I want to make it a unit quaternion, so I'm going to go cosine theta plus sine theta I. So this is going to be my Q that I'm going to use to rotate. So my Q inverse then is just cosine theta minus sine theta I. And I want to see what does it do to J. So I'm going to find FQ of J. Okay, well, let's do it. So I think about J as being a quaternion, and then I multiply. And then times J. And then I'm going to multiply that by cosine theta minus sine theta I. Okay. Well, the first one's easy. Cosine times J is just cosine J. And then sine theta times, so I've got sine theta. If I do I times J, dot product 0, I mean, everything's 0. Basically, basically all I got is what is I cross J? I cross J is K, right? Okay, so that's the first one. Then cosine theta minus sine theta I. When I do this guy, I have a little bit more. So cosine's going to multiply both, so I'll wind up having cosine squared J, and then sine theta, cosine theta, K. And this one I'm going to have to do the cross products again. So I have sine theta, cosine theta. J cross I is minus K, and then there's another minus right here. So minus minus makes a plus, so this will be plus sine theta, cosine theta, K. And then here, K cross I is J. So I've got minus sine squared theta, J. So if I look at my J's, I have cosine squared minus sine squared, which we learned in trig, that's one of the ways we can find cosine 2 theta. And same thing, if I look at my K's, I've got 2 sine theta cosine theta, which is sine 2 theta. Okay. So what is this? Well, if I graph just the JK plane, I started here at J, and then I rotated 2 theta to the point cosine 2 theta, sine 2 theta. So if I have Q as my cosine theta plus sine theta I, this one is rotate about the I axis angle of, not angle of theta, but angle of 2 theta. Okay? And same thing, if you did any other vector, so this happened to be I, but any other unit quaternion can be written as cosine plus sine theta times a unit vector. So this would be rotate about the line through this unit vector by angle 2 theta. Okay. So sure enough, these funny conjugation maps, I mean, these x goes to q, x, q inverse, these give you all the rotations of 3D space. And it's kind of strange because, well, actually, just as I go from theta 0 to pi, I get all the rotations. And then I get them all again from pi to 2 pi. Right? So it's a little surprising that not only do I get all the rotations, I get them all twice. And this is going to get into something that's like incredibly whatever, and I'm not going to talk about it. But so basically the picture we get is the unit quaternions. They're the 4-dimensional sphere. So this is the 4D sphere. And I'm going to throw in something we didn't talk about, but just for the chagrins of it, this is, you'll see this in later courses. I'm not going to talk about it, but this is something called the first special, the lowest dimensional special unitary group. Okay. This is the double cover of SO3, which SO3 is just, that's the notation for 3-dimensional rotations. But the important thing is this S4 double covers the SO3. And what does that mean? Well, it means that the world is weirder than we think it is. But you've seen this before if you took physics or chemistry and you learned about electrons. Well, somebody probably told you at some point, if I take an electron and I rotate it 360 degrees, you would think you get back with the same thing you started, but you don't. You get the electron winds up having the opposite spin. And that's actually what's going on. Even though we think our world is three-dimensional real space, and so these three-dimensional rotations should be all the things that can happen, it actually winds up that, I mean, when we think about S4 acting on 3 space, it's like, oh, well, we get all the rotations twice. Well, actually, those 2 different rotations, I mean, we actually get 2 different things. So, and the difference, you don't see them on normal matter, but if you look on electrons, those 2 rotations actually give the 2 spins. I mean, so those 2, let's say the 2 copies of that rotation actually give the 2 spins of the electron. But again, that's like way, way beyond the scope of this class. So I'm not going to even hope to explain what all that means. But that's what I wanted you to see, though, is that these conjugation maps, you really do get all the 3-dimensional rotations. Believe it or not, you actually get them all twice. And that's, in some weird way, that's where electron spin comes from, is the fact that you get them all twice. But anyway, hopefully that made some sense. It probably didn't, but hey, it's good to see it, and maybe you'll understand it somewhere down the line.